E or X is just a vector bundle. And theta will be a twisted, that's why we call it twisted, will be an endomorphism of E, but we twist by this line bundle D. Vector bundle theta is a morphism of OX modules. Okay, and so such a pair, so we will want to consider families of them and consider the moduli spaces, and for this we need a notion of stability. So a pair E and theta is stable or semi-stable if for every subbundle so every F is not 0 and not equal to E, a subbundle. That is, and we assume that it's preserved under phi. So the image of here, it should lie in the image of F tensor D. So given such a subbundle, we require that the degree of F, if you look at this quantity, divided by the rank, so it should be strictly less if we want the bundle to be stable. And we also allow equality if we just want a semi-stable bundle. A first sort of numerical observation is that, of course, if the rank of E and the degree of E are co-prime, then semi-stable is equivalent to stable. Simply because if these things are co-prime, you cannot have something of smaller degree having the same, exactly the same ratio, which is sometimes called the slope. So this condition, rank and degree co-prime, is sort of it's a recurrent condition that we will encounter many times. So now we can consider moduli spaces of these objects. So there will be two different notations. So this sort of bold M RD. So it also depends on X and on the divisor D, but I will not write this. So this will just be the moduli stack of semi-stable pairs E theta with rank of E equal R and the degree of E to be D. And then the usual M RG, it will be the coarse moduli space of the same semi-stable object.
Sorry, Dimitri, just a question. So those two letters M, they are supposed to be different M's, or
yes.
How is it?
Let me make it more clear. So M, like this. Okay, great, thanks. And there's a map this way, which is why M is the coarse moduli space. So certain things will be identified. If you know this notion of S equivalence, or saying two semi-stable bundles are equivalent if they have the same associated gradient, basically. So you have these two objects, and and we record some simple facts. Well, not, maybe, I don't know if simple, but let's record some facts about their geometry. So first, there is a role that this degree plays of the line bundle we twist with. So we will consider basically two cases. So either the degree is strictly bigger than 2g minus 2, the degree of the canonical bundle of the curve. And in this case, this stack MRD is smooth for all pairs R and D. And again, and still in this case, the space MRD is smooth exactly when R and D are equal to 1. Okay, so the stack, so sort of smoothness for a stack is a statement about deformations. And in this case, if the degree is larger than the canonical, then these are unobstructed. And the stack is just always smooth, but nonetheless, if we have strictly semi-stable objects in our stack, then the coarse moduli space will not be smooth. So only in the coprime case, we have smoothness. And the second case, if D is the canonical bundle of the curve, so that's usually, I mean, somehow these are the usual Higgs bundles. Then MRD and MRD are both only smooth if, well, I can ask before, if R and D are coprime. So in the case of the canonical bundle, the stack can also be singular. It will be singular in general if you don't impose this coprimality condition. And so from now on, we'll assume that, I mean, our D is either of strictly bigger degree of 2G of degree bigger than 2G minus 2, or D, we take it to be the canonical bundle. So we have the following theorem. Which was, I think, conjectured by Hausel and Rodriguez-Villegas first. So it has now many proofs. So maybe Mellit, Anton was the first, and it's you. Then it's the three of us, so Gröschenik, myself, Ziegler. And then also now Maulik and Shen. I'm not sure, yeah, I'm not sure exactly where to locate, but they have a series of papers, and I'm sure they can prove the following statement, that so for D and D prime, two integers such that both are coprime to the rank. So both coprime to the rank. Given this case, the Hodge numbers of this, so these will now be smooth spaces, so smooth algebraic varieties. And they have the same Hodge numbers. So sort of similar in Battir's theorem, but we don't know. I mean, they're certainly not projective, but not sure if they're rational or not. And also, there are basically four different proofs of this statement. Mellit's proof is combinatorial, so there are actually formulas for this. Which I go back to Schiffman, but Mellit sort of so there are formulas that involve D, but then one can show that the D doesn't play a role. He used, I don't understand quite, but he uses some automorphic considerations, automorphic forms, some counting also. So the proof I want to give in a minute, explain is again using p-adic integration. And Maulik and Shen, they use perverse sheaves and the Hitching vibration. And so in this case, our approach and theirs are similar, that we both rely on the so-called Hitching vibration. So this will not be the, I mean, you see the proof will be quite short of this. The statement, so the main point of my talk is then how to generalize this to the case when R and D are not coprime. But let's first look at the coprime case. So we need to introduce the Hitching vibration. So this is a certain morphism H R comma D, which goes from the moduli space, but of course we can compose it with the map from the coarse moduli stack to the Hitching base, which we know by A, which is the following affine space. Global sections of the various powers of this line bundle that we fixed. So what does it do, this map? So if we take a pair, a Higgs bundle, theta, we think of it as being an endomorphism of the bundle. So locally, it's given by a matrix, or you can think of it as a matrix with coefficients sections in D. And so if I take the characteristic polynomial of this matrix, the coefficients of that characteristic polynomial will exactly live in these different, will be global sections of the different tensor powers of D. And so we get a well-defined map like this, which is called the Hitching vibration. And the reason this is so useful is that the fibers of this map can be analyzed quite precisely. So to any A in this base, so this is the characteristic polynomial, one can associate what is called a spectral curve. And the spectral curve is a certain curve X, say A, which covers the original curve X we started with itself. It lives in the total space of the line bundle D, and it's basically the curve cut out by the equation given by the characteristic polynomial. So another way to say is that this is a ramified cover of degree R. So generically, over the curve X, there will be R points of the curve XA. And these R points, they correspond exactly to the roots of the characteristic polynomial you get by evaluating all these sections at that point, generic point of X that you chose. And then, of course, there are special points on X where the characteristic polynomial has multiple roots, and so you get in general a ramified cover of the curve. But generically, one can show that this curve XA is smooth with our assumption. So we write A smooth inside A where X comma A is smooth. This will be important for, again, in this integration business. So, okay, so one has this curve, and now the point is that one can identify, so for a point in this smooth locus, one can identify this fiber simply with the pick, so with line bundles of degree d on this spectral curve. Okay, so it gives sort of so in particular the fibers. So in this generic case, the fibers are abelian in some sense, or torsors over abelian varieties, which is what we will we will use a lot. So that's why this is so you should think of this pick D, that this is an extremely nice space somehow, whereas a priori the fiber of this Hitching map we would not maybe know so much what to do. And the map, so the identification is basically for a line bundle, you just push it forward along this degree R map, and then the push forward will be a vector bundle of rank R, and you have a canonical section coming from the fact that the total space of T has a coordinate function. And so you get this correspondence. So in general, if you're not in the smooth locus, the fibers will be sort of compactified. So compactified Jacobians. In particular, the Hitching map is proper, and the fibers are some sort of compactified Jacobians, which is guess why there's all these relations with, so compactified Jacobians, then they relate to Springer fibers and affine Springer fibers and so on. So that's why these spaces appear so often in maybe in geometric representation theory, I would say. And so now what we want to show is that for different T's, okay, to prove the theorem, we want to compare, as in Batyref theorem, Hodge numbers for different degrees, and so one way, or the way I introduced to do this, is to compare the volumes of these spaces. So we can again just spread out. And show the following. So we want to show that the integral over O points with respect to the canonical measure for R and D is the same as the integral with respect to the canonical measure of MR D prime. So also O points of this. So again, the spreading out, you can pass to finite fields and then to some p-adic field. You can also, another way of thinking is instead of starting with a curve that is smooth over the complex numbers, this X, you start with a curve that is smooth over this ring of integers O. So you just spread out that curve and the line bundle D that comes with it. And then you can just construct the same moduli. I mean, then you have the same moduli problem over O, and you construct the moduli space, and that's the space you get. And if you can show this equality for all ring of integers O and all R and D, then you will get the statement of Hodge numbers on the complex curve. And so that is basically again this Wales theorem that tells us that this equality will be enough. And now what is new is that we will consider the map to the Hitching base, or the O points of the Hitching base. And instead of showing this equality directly, we will show it, well, we show a stronger statement, we will show it fiberwise, basically by by Fubini. It's enough to show for if you pick a point in the base, and again, by this measure zero business, we can consider only those points in the base that generically lie in the smooth locus. And then we need just to compare volumes of the fibers here. So H inverse RD O. And here H inverse RD prime of O. So we need to compare this, and now we can use this geometry. So H RD inverse Y, sorry, it should be A here, and then O points of that, and also A here, O points of that. And now, so first, one thing we notice that, as I said, the Hitching map is proper, and so the O points, I can replace them by the F points, which helps me in the sense that now over F, this A was in the smooth locus. And so now this thing, I can just identify it with pick D prime of XA F. Okay, so somehow I only care about the generic fiber of my point A, and there the Hitching fiber is just the pk, and not this. Because the special fiber will be very complicated. Could be some sort of compactified Jacobian, but the generic fiber is okay. So I get some sort of abelian variety over the ring of integers, over just this p-adic field. And I want to compare these two. Now, I haven't said much about the measure, and for simplicity, let's not go too much into it. But basically, on any abelian variety, there's not so much choice. There's the canonical bundle is trivial, and global sections are all constant. So there's up to some constant. There's basically one section one can choose, and then one can show, this is not so difficult, that for different degrees T and T prime, you can choose them compatibly. So what does this statement, what does this now look like to prove this? And so it turns out that this is now a purely arithmetic statement that we show, because, so notice that we're in the following situation. So F is not an algebraically closed field. And so either what happens is that this pick D prime XA of F, it will not have any rational point. We have no point.
Sorry, there is a question. So if you don't have the mic, maybe use mine.
Sorry, it's just a stupid question. So what would happen? How did you pass from O to F in those fibers? I mean, before you had integrals with O's, and now you have with F, so it's the kind of, there's a formula to pass in between those? Or?
Yeah, so it's this observation. Let me write it here. It's simply when, for any, if you have any variety, say X, no, X is not good, we had it already. So Y over O proper, then the O points of Y are the same as the F points of Y. And for us, Y would be this fiber. So this Hitching fiber, which is proper. Okay, thanks. So it's not, yeah. Well, you use properness, which is kind of a very structural result for Higgs bundles, but not more. Okay, so this pick D prime XA. So what? It's a torsor for the pick zero. It acts on it transitive, simply transitive. So either there is a line bundle of degree D prime. So either there isn't, then it's empty, and in this case, in the empty case, the integral will be 0. There's just the manifold is empty, or there is a rational point. And in this case, we can use this rational point to establish an isomorphism between the peak zero. So once we have one, then we can just act with all the others. And the same is for, of course, for the D. So in order for this equality to be true, basically what has to happen is that either both sides are empty, then we have 0 is equal to 0, or both sides have a rational point. And then we just integrate the same, I mean, it's just the same volume on it's just the integral over peak 0 on both sides. So we need to check that it cannot happen that one side is 0 and the other not. So need to check that say is empty if and only if pick D prime if and only if this is empty. And now the observation is not so difficult, but it's purely arithmetic, which I think it's very pretty. So we always have, so since the base curve over O is smooth, we have that the base curve itself, it has a section. So this is so you can, I mean, you have a point over the so a smooth curve over finite fields have points, and then you can lift them to an O point by Hensel's lemma again. And so this having a point in particular implies that pick one of X F will be non-empty. So a point will give you a degree 1 line bundle on your curve. And so then you can pull back along this spectral map, and you see that then you have a degree n line bundle on F. Always, right? But now there exists certainly an integer e such that d times e is congruent to d prime mod n. Both are co-prime to n, so we can make one to the other. And so this implies that, say, if pick d has a rational point, have a line bundle, then I can just take its e's power, and then the e's power, and then it will be of some degree that is co-prime, that is sort of congruent to d prime, and I can use the degree n line bundle I already have to construct one like this. And vice versa. And in the other way also, so if pick d prime has a rational point, I can use the same construction to get one for d. So we see that they have rational points exactly, one when the other has. And so that proves this degree independence by some curious observation. It's some simple arithmetic in the end. But it's very clean, and we use very little of the geometry of the Higgs moduli space. And that is what is so curious about. And so for a while we didn't quite know what, I mean, it's a nice result, and we didn't know what to do in the case when R and D is not co-prime. So there's a question of Camilla, I think.
Dimitri. Okay, sorry. So here you just integrate on smooth on the fibers over the smooth locus. I mean, where do the supports disappear? I mean, my question is, in the decomposition theorem, of the related to the Hitching vibration, you know that you have contribution from supports which are not in the smooth locus. So how are, but of course in the Hodge numbers you should recover the whole cohomology. So where does these supports go? I mean, how are they taken care by the integration?
Right. So there is no relation between what we do and supports. There's no way for us to see supports in any way I know. But it seems to me that for the total sort of cohomology, maybe the supports don't really. I mean, they matter if you want to apply the decomposition theorem, but you know, for that the cohomology of the total space, in some sense, they don't necessarily matter, right? It's just if you want to apply the decomposition theorem, but for us, this doesn't. Yeah, fortunately or unfortunately, it doesn't appear. And in particular, we don't see a difference between the case when the degree, when this line bundle D is the canonical or of higher degree. The proof is exactly the same. So, and for as far as I understand, the decomposition theorem is much more difficult if D is the canonical bundle, whereas D has high degree. And so this is one curious thing about this integration. Yes. Okay. Thanks for the question. So
can I make a comment? Not a question, just a comment. So I think what you should emphasize is that even though you look at smooth fibers over, I don't know, QP or something, but the fibers are actually singular over FP. So somehow your thing is looks like small, but in fact it's pretty big. So it goes around the singular fibers of the Hitching map over FP. So you should make sure that people have the wrong impression that you are only over the smooth locus where the easy things happen, but somehow over FP you actually you have singular fibers.
Yes, right, thanks. Right, it's yeah, let me just, okay, so let me stress again, this is the arc space we're looking at. And so the arcs, they will end in all possible fibers everywhere in the whole Hitching space and the Hitching base. And so we see everything, but it's just that certain properties like the volume, one can read off uniquely from the generic parts of these arcs. And we don't necessarily need to understand how the locus looks where they end. That's yes, thanks. Okay, so what about the case when R and D are not coprime? So then the modular space is singular, and somehow the cohomology is not that meaningful for a singular space. So there is an extension here. An extension of the theorem, which is again proven by Mellit combinatorially. If we replace let's say Hodge. Okay, I before I say Hodge numbers, now let me just work over for simplicity. Let's just work over a finite field. Then the analog of saying the Hodge numbers were just this number of points that we had to control or to compare. And so we want to replace them by and I never know how to call them, let's say BPS invariants. Let me write omega R and D. for these. So there are, yeah. So you can think of them just as numbers. So that there's of course a very rich and deep theory, and it's not clear in general how to define them. So for Higgs bundles, one can give an ad hoc definition. Which basically goes as follows. So for any rational number mu, they are defined by the following relation. So generating series, basically. So you look at the quotients d over r that equal this rational number mu. And then you count points of the stack of Higgs bundles. There is some correction, okay, some q power here, which doesn't. So okay, let me say it's some q power depending on r and d, and two coefficients, two variables keeping track of r and d. And you declare that those be the same as the platistic exponential of a sum over r and d of the generating series of these BPS invariants. And so recursive, so sort of this, so what does this exp do? So exp, so for any variety, say z over fq, so exp of z times some variable, say okay, w, it will just be the Weyl zeta function of t. Okay, so this is, I mean, if you have never seen this, it's probably not so helpful. There's some way to define this omega rd, and you can convince, okay, it's not so hard to convince yourself that if, sorry, this should be also d over r equal mu. You can convince yourself that if d and r are coprime, then you can already see from this formula that omega r comma d is just the number of points of the moduli space as before, times q to some power alpha. Okay, but in general, I mean, in general, it will be more involved. They will sort of, to compute omega RD, you will have contributions from MRD of smaller rank and degree that contribute. But so this turns out to be a sensible invariant. And so the theorem is that to Melid is that omega R and D. So again, he finds a formula and he shows this is independent of D combinatorially. And so when we proved with Michael and Paul this degree independence for Higgs bundles, we were sort of basically by the work of Tamás and Michael Tadeusz, we knew that we could also adapt our result to say something about the volume of the singular moduli spaces also being independent of the degree D. And but we never really wrote it out, and it wasn't clear how, I mean, what should we do with such a result, because it would be some obscure integral, and we don't know how to relate it. And it was only now recently that I realized that this sort of thing we do, so these integrals we write for singular moduli spaces, they're actually very natural, and they generalize to many other situations where such an independence is also expected. So so let me state what we found. So this is now with myself. So I call it a theorem. It's more of an observation. So there exists sort of natural, and I will try to explain where these natural functions come from. Which live on this coarse moduli space on the O-valued points, and they are complex valued, such that if you integrate them then the corresponding integral will be independent of the and this is for all D and D prime, independent of whether they are co-prime or not. And also, so if R and D are co-prime, then these functions are one constantly, and we get back the previous thing. So in part, so in particular, we see that these BPS invariants, this omega R and D, they will always, well, by Anton's theorem, they will be given by our integrals of O. But I don't know directly why this is true, but comparing ours and Anton's theorem, this is sort of true. And the second remark is, so this generalizes to say of one dimension to moduli spaces of one-dimensional sheaves on, say, toric del pezzo surfaces. And so in this case, there was a recent paper by Maulik and Chen, where and they also showed that in this case, these BPS invariants, so in this situation, one talks about, I mean, the invariants are not rank and degree, but there's a curve class and Euler characteristic. So where Maulik and Chen showed that omega, beta, and chi are independent. And so again, one can define our integrals over their spaces, over these moduli spaces of one-dimensional sheaves with these functions, and again, they will compute the BPS invariance in this case. And so now in the last 2 minutes, I'll give the definition, and you will see in many cases when one can define these BPS invariants, our functions also make sense, and could hope that this is a general phenomena. So let me just say how to define F, R, and D. So and what is nice, but also a bit puzzling, is that the construction is very arithmetic. So it doesn't, for example, in motivic integration, I don't know how to define it. So one has to consider the open substacks or subspaces of stable Higgs bundles. So let me do it like this. So strictly, so if R and D are not co-prime, they will be strictly contained in the stack. And then we have maps to the course moduli, and here also M. And here, this is something one calls a GM Gerb. So it's basically sort of they have the same points, just the automorphisms. So stable bundles, they have scalar automorphisms, and the only thing that changes from the stack to the space is that we make these disappear, and this is this map. And so a Gerb, so GM Gerbs, if you don't know what it is, they are classified by the second Cohomology with values in GM. So just like so, if you take GM torsors, they're classified by H1. These Gerbs are classified by H2. And so if I call this Gerb alpha, so the space of stables with the map, then I get a map. Alpha induces a morphism. So let's say F alpha from the whole moduli stack. But again, sort of we can assume that generically the generic point will lie in the stable locus, and we get a map to the complex numbers as follows. So we pick a point X in here, and then we send it to the class of the. So I now just think of it as the generic point, and I pull back this Gerb, which is basically a class in H2 of the field F. Values in here, and so this is you can identify with the Brouwer group of a non-Archimedean local field. You can identify it with Q mod Z, which then you can embed into the complex numbers by the usual by choosing its generator e to the 2 pi I. So identify this with roots of unity. So you get a function F alpha, which takes values in the roots of unity, and so we said F RD to be this function F alpha. So it's somehow the Gerb that measures the difference between the moduli stack of stable objects and the moduli space of stable objects. So it's a very natural object that exists for one-dimensional sheaves, but in principle exists also for quiver varieties and so on. And the integrals have the right invariance properties. And so whenever you know that the BPS invariants are invariant, then you know a fortiori that also that our integrals will compute those invariants. And so now we just don't know why, but that's what we try to understand next. So that's all I wanted to say.
Well, thanks a lot. Okay, so thank you, Dimitri. One thing before we ask questions, would you mind sharing with us this file from your pad? Or I don't know how difficult or easy it is. So if you can, so please paste it again in the chat. And in the meantime, I would like to ask for questions and now indicate to me, right, so Tamas?
Yes, so I didn't get it. Could you also remove the Schmaulich-Shen thing with this arithmetic understanding of the BPS invariance?
Not yet, because we don't know. We just know that our integrals are invariant, and that in the coprime case they compute the number of points, and the same is true for the BPS invariance. But I have no direct. One would need a direct proof that in the singular case our integrals compute the BPS invariance.
So can you go back a little bit where the
comments? I see that Camilla, would you like to ask a question? So you need to unmute yourself.
Okay. So do you think that your methods, your generalization to the non-coprime case might be applied to prove the topological mirror symmetry in this case?
So that is when you take intersection cohomology instead. So I think in the one, so I think what we do is sort of more directly related to this BPS invariance, and they will agree with the intersection cohomology only in this case where the degree is strictly bigger than 2g minus 2. And for the canonical bundle, they're not the same as I learned now. And so I don't know how we can access it in the case of the canonical bundle. I don't see how we can relate the integrals to the intersection cohomology. But in the other case, yeah, it's sort of would be equivalent if there is such a statement.
All right, so more questions or comments, please either let me know
Tamas has another question
in the lecture hall or raise your electronic hand. So how is it? Sorry, I didn't get your feedback, Dimitri. You can share that file or no?
I can, yeah, I can share it. I need to print. I don't know if I can print it to a PDF while I'm in presentation mode. But I can definitely send it to you.
Maybe you can also just then, after the talk, send it to me, and people who want it, they can write me an email. I will distribute it if you want, or maybe they can write directly to you, or maybe, yeah, now if you can put it, if you can share it.
I share it in the chat.
That would also be great.
I share it in the chat, but you have to wait like 1 minute or two to get it. It's kind of slow. Okay, here it is. Okay, it's coming, it's coming. So we go to the, I think I have to stop share.
So while this happening, can I then ask maybe another question? I mean, it's the continuation of my previous one. So in this case of the piezo surfaces,
yes.
So you define this function, right?
Yes.
And can you show that integral, that twisted volume, is independent of well, I don't know what the chi or in that case,
yes.
in the
yes.
piezo, okay.
So I can show this same theorem here. So this theorem with Carocci and Orecchia.
Mm-hmm.
Yeah, it's also true in the Del Pezzo and also in the K3 case.
Right, but what, do you have Hitching fibration there, or how do you show the independence of
yes,
the
yes. So there is a sort of Hitching fibration where you you send a one-dimensional sheaf to its support.
I see.
Yeah.
And you have the same abelian varieties and
yeah.
Mm-hmm.
So the statement, so I haven't explained how you prove it, but it comes to some, so generically this Gerb is just the Picard stack and over the Picard space, this Picard variety. And then there is a sort of, it's a duality between Gerbs on an abelian variety and torsors over the dual abelian variety, and it just works out. Just as in the topological mirror symmetry. The dual Gerbs you had, I think are similar to this. Okay, I think I shared the file.
So thanks a lot. Now we got your file, and I don't know whether there are any other questions or comments for Dimitri. So nobody raises the hand. So then, Dimitri, thanks a lot, and sorry for those complications with the sound, right? If we want to speak, we don't hear you. So thanks a lot.